Let's start with another sorting algorithm under divide and conquer strategy, that is quick sort algorithm. So we discussed a merge sort, so now we will be discussing quick sort. So the idea behind merge sort was the given array of size n was divided into array of size, two different arrays of size n by 2. Now this array of size n by 2 was again divided into two different arrays of size n by 2. Same case is here, two different arrays of size n by 4. And now this process continues till we remain with array of size 2. So this is the strategy behind merge sort, or we call divide conquer strategy, that is a merge sort strategy. So now this strategy was efficient enough so that in most of the cases we were having complexity of big O of n square. This complexity was getting reduced to big O of n log n. So when array size is bit smaller and if we apply merge sort, it follows all the steps in case of merge sort. But now if we have a smaller array size, then quick sort works efficiently compared to the merge sort. So let's discuss what quick sort does. So let's say you have array of size n. Okay, so if you have array of size n, so I'll just denote array like this, which has some elements. Let's say some elements like this. I'm just showing it a dotted line. So now on these elements it chooses one pivot element. So I'll write pivot element 1. So now this array of size n will be divided now into two different arrays, but size may not be n by 2. So whatever pivot p1 I am choosing, so to the p1 left side of p1, to the left side of p1 I will be taking the elements in that array which are less than p1, and I will be taking elements which are greater than p1 to the right hand side, so that I will be getting one array here and one array to the left side. Now again in this array I have to choose another pivot which could be, let's say, p2. So now again this p1 will be divided in such a way that you will have array elements less than p2 in another side and elements which are greater than p2 in another array. Then here also, if you will say that p3 is the pivot, then less than p3 will be left hand side, greater than p3 will be right hand side. So this process again continues till we just go on sorting this. So to understand it better, let's take the example which we have chosen, and we'll discuss how the pivot plays a role in quick sort. So the example which I'll be again choosing the same which we discussed in merge sort. So 8, 9, 6, 5, 3, 12, 4, 10 and 7. So now we have this array of size 9, right? So we have array of size 9. So now we have to choose one pivot element of this from this array. So right now I'll just choose pivot is equal to 7, and let's discuss what will happen. So when I'm choosing pivot as a 7, so the elements which are less than 7 will fall in this. So is 8 is less than 7? No. So 8 is greater than 7, so 8 will go here. Is 9 is less than 7? No. So 9 also will go into the left hand side array. Is 6 is less than 7? Yes. So 6 will fall here. Is 5 is less than 7? Yes. So 5 will go here. Is 3 is less than 7? Yes. Then 3 will go here. 12 is less than 7? No. 12 is greater than 7. So we will go 12 here. Then 4 is less than 7. Then 10 is greater than 7, and already 7 is our pivot. So you can see that as we have chosen 7 as a pivot, we have divided that array of size 9 into two equal arrays of sizes 4. So the pivot element again will be saving some of the time. Just we are choosing the pivot randomly. If you choose the pivot, any pivot, If you choose the random pivot, there are again some drawbacks. If you choose a pivot which is a center point, there is an advantage. We'll discuss both the cases. So now this 7 is a pivot and it is actually a center point. Now in this, let's choose pivot as 5. So now if I choose 5 as a pivot, so the element less than 5 is 3. Like 6 is greater than 5, so 6 will go to the left hand side. 3 is less than 5, so 3 will go here. 4 is less than 5, then 4 is like this. Now we'll choose pivot here as 10. So now 8 is less than 10, 9 is less than 10, and 12 is greater than 10. Now if you just compare 3 and 4, 3, so now you can just see, if I now go reverse way, it is already sorted array. So 3, 4, then 5, 6, then 8, 9, 10 and 12. So this is the fastest way of sorting a smaller size array. But the drawback with this example or with this technique, which is a quick sort we are saying, the drawback is, let's say, I'll just write down the array again, 8, 9, 6, 5, 3, 12, 4, 10 and 7. Let's choose 3 as a pivot. So if I choose 3 as a pivot, the element less than 3 will fall here, element greater than 3 will fall here. So what, 8 is less than 3? No. 9 is less than 3? No. 6 is less than 3? No. 5. So you can see all the elements which are greater than 3. So I'll be just going with 3, then 5, 12, 4, 10 and 7. Now again from this, if you choose some random pivot, let's say 8 only will be chosen as a pivot. I will just go ahead. We'll just go on choosing the first element now on for this. So 9 is less than, greater than 8, 9 will fall here. 6, then 5, 12, 4, then 10 and 7. Now again from here choose 6 as a pivot. So 5, 4 and 7. Here choose 9 as a pivot, then you will be getting nothing here, and here you will be getting 12 and 10. And now again you can see 5 and 4 are not sorted, so at this stage you have to sort 4, 5, then the pivot was 6, then 4, 5, 6, 7, then here pivot was 9, but 6, 7, and then I should take the center point 8, then it is 6, 7, like after 8 it will come 9 as a pivot, then 12 and 10 should be sorted, so it will be 10 and 12. So you can see that as I have taken the pivot point 3, which is to the most smallest number, then the process extended little bit longer. Now again, let's say whatever we have solved here, I'll just change the pivot in each case. So now I'll choose the pivot here 4. What will happen? There is nothing is less than 4, so it will be again go on sorting like this: 8, 9, 6, 5, then 12, 10 and 7. So now let's choose pivot as a 6. So if I choose 6 as a pivot, only 5 will go here, all other terms will go here: 8, 9, 12, 10 and 7. So you can see that the levels of the tree are going on increasing if we miss the choosing of the pivot, and we are traversing over the array more number of times. So the quick sort is efficient. Quick sort is efficient if we choose pivot. If we choose pivot as a center point or near to the center point, as a center point or near to the center point, then quick sort is efficient. Else it is not that efficient. And you can observe that whenever we choose pivot as a center point, in this case, every time we have divided the array into 2 equal half, nearly 2 equal halves. So what does that indicate? This array of size n was getting converted to the array of size near to n by 2. So array of size n was getting converted to the array of size near to n by 2. So its recurrence relation we were getting as T of n, which is equal to 2 times T of n by 2 plus n. So in this case, the complexity of the algorithm lies as big O of n log of n. So the best case in quicksort and best case complexity is big O of n log n. In case of worst case, so worst case will be every time we'll be choosing a smaller pivot point. So actually speaking, the array of size n was getting divided into array of size n minus 1. Again next time I'll be getting array of size n minus 2, because we are getting one-sided tree and this side nothing is there. So I have n elements in the array. So one pivot and remaining n minus 1 elements will be going into another array, and every time I am traversing over the entire array. So the recurrence relation for this worst case, so I will be writing worst case. So for worst case, the recurrence relation could be T of n, and the problem was of size n was getting converted to problem of size n minus 1, and to convert that you have to traverse over the entire array, so required time is n. So now if you remember recurrence relation solving example 4, we have solved this example which was leading to the complexity of big O of n square. So for quicksort, see, for merge sort we discussed merge sort, every time we were converting array into n by 2 size, so its complexity will be always big O of n log n. But for quicksort we have two different complexities. One is best case, and best case complexity is big O of n log n, which is quite similar to the merge sort. And worst case complexity, which is big O of n square, which is quite similar to again one of the algorithm like bubble sort or quick sort, selection sort, or maybe insertion sort. So now you can see the worst case complexity is big O of n square in case of quicksort. So the main problem is choosing the pivot in quicksort, and when array size is larger, another drawback of a larger array size, the worst case may not converge with quicksort. So the issue of convergence also will be there with the quicksort. So merge sort is always better in case of large size array, and small size array, if pivot is chosen properly, then quicksort is efficient compared to the merge sort, because as we discussed, you can see that one element, the pivot element, will not be counted into the array size in most of the cases. Okay, so this is with the quicksort. Thank you.